Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. The landscape of early 19th century mathematics resembled a vast, uncharted territory, ripe for exploration and conquest. Among the intrepid pioneers venturing into this unknown domain, Carl Gustav Jacob Jacobi emerged as a formidable figure, driven by an insatiable curiosity and a relentless pursuit of mathematical truth. His early career unfolded against a backdrop of intense intellectual ferment, particularly in the burgeoning field of elliptic functions, a realm where he found himself locked in a spirited race against the brilliant Niels Henrik Abel. This competition, far from being a mere rivalry, served as a catalyst, pushing both mathematicians to new heights of creativity and innovation, ultimately reshaping the course of analysis. Jacobi's journey began in Potsdam, Brandenburg, where he was born into a Jewish family. Even in his youth, his prodigious intellect was evident. He absorbed knowledge with an almost uncanny speed, quickly mastering classical languages, history, and mathematics. His exceptional abilities allowed him to bypass several grade levels, directly entering the upper class of the Potsdam Gymnasium. However, the rigid structure and the delayed exposure to advanced mathematical concepts proved frustrating for the young Jacobi, who was already delving into the works of Euler and Lagrange on his own. This self-directed study fueled his passion and laid a solid foundation for his future endeavors. In 1825, Jacobi presented his doctoral dissertation at the University of Berlin, focusing on the theory of rational fractions. This work, though an early effort, already showcased his analytical prowess and his ability to tackle complex problems with innovative techniques. Rational fractions, expressions formed by dividing one polynomial by another, were a subject of considerable interest at the time, appearing in various areas of analysis and algebra. Jacobi's dissertation provided new insights into their structure and properties, demonstrating his mastery of the existing theory and hinting at his future potential. Following his doctorate, Jacobi's academic career gained momentum. He secured a position as a lecturer at the University of Berlin, where he began to attract a following of talented students. However, the intellectual climate in Berlin, while stimulating, did not fully satisfy Jacobi's aspirations. A more conducive environment beckoned from the east, the University of Königsberg. The move to Königsberg proved to be a pivotal moment in Jacobi's career and a turning point for the university itself. Königsberg, a city steeped in history and intellectual tradition, was undergoing a period of significant academic growth. The university, founded in the 16th century, had long been a center of learning, but it was now poised to reach new levels of prominence, thanks in part to the presence of exceptional faculty members such as Friedrich Wilhelm Bessel, a renowned astronomer and mathematician, and Franz Neumann, a physicist known for his work on elasticity and optics. Jacobi's arrival in Königsberg in 1826 injected a new dynamism into the university's mathematical community. He quickly established himself as a leading figure, attracting students and colleagues alike to his lectures and seminars. His teaching style was characterized by its clarity, rigor, and enthusiasm, inspiring a generation of mathematicians to embrace a more analytical and abstract approach to their work. Under Jacobi's influence, along with the contributions of Bessel and Neumann, Königsberg transformed into a world-leading center for mathematical physics and analysis. The three professors fostered a collaborative environment, exchanging ideas and challenging each other to push the boundaries of knowledge. Bessel, with his expertise in astronomy and applied mathematics, provided a link to the physical world, ensuring that the theoretical work being conducted in Königsberg had practical relevance. Neumann, with his deep understanding of physics, further strengthened this connection, creating a vibrant interdisciplinary atmosphere. Jacobi's contributions to the Königsberg School extended far beyond his individual research. He played a crucial role in shaping the curriculum, introducing new courses on advanced topics such as elliptic functions, number theory, and differential equations. He also encouraged his students to engage in original research, providing them with guidance and support as they tackled challenging problems. This emphasis on research and innovation helped to cultivate a new generation of mathematicians who would go on to make significant contributions to their fields. The atmosphere at Königsberg was one of intense intellectual activity. Jacobi, Bessel, and Neumann held regular seminars where they presented their latest findings and engaged in lively discussions. These seminars attracted not only students and faculty from the university, but also visiting scholars from other institutions, further enhancing Königsberg's reputation as a center of mathematical excellence. The focus was always on rigor and precision, with an emphasis on developing new methods and techniques for solving problems. The Königsberg School distinguished itself through its commitment to a rigorous, analytical style of mathematics. This approach, which emphasized the importance of precise definitions, logical deduction, and abstract reasoning, contrasted with the more intuitive and geometric methods that were prevalent in some other mathematical centers. Jacobi, in particular, was a staunch advocate for this rigorous approach, believing that it was essential for achieving a deeper understanding of mathematical concepts. He instilled this philosophy in his students, training them to think critically and to demand clear and convincing evidence for all mathematical claims. The impact of the Königsberg School on the development of mathematics and physics cannot be overstated. It produced a remarkable number of talented mathematicians and scientists who went on to hold prominent positions in universities and research institutions around the world. The school's emphasis on rigor and analysis helped to shape the direction of mathematical research for decades to come, influencing the development of fields such as complex analysis, functional analysis, and mathematical physics. The seeds of this transformation were sown in the fertile ground of Königsberg, nurtured by the collaborative spirit and intellectual leadership of Jacobi, Bessel, and Neumann. From this vibrant intellectual ecosystem at Königsberg, Jacobi would launch his first great assault on one of the most stubborn fortresses in 19th-century mathematics, the theory of elliptic integrals. For generations, certain fundamental problems in geometry and mechanics had resisted closed-form solution. While the circumference of a circle yielded the constant pi and the area under a parabola was a triumph of Archimedes, the seemingly elementary question of calculating the precise arc length of an ellipse remained elusive. A similar difficulty arose in physics when attempting to find the exact period of a large amplitude pendulum. In both cases, the calculations led to a class of integrals that could be evaluated only through laborious, infinite approximations. These were the elliptic integrals, so named for their origin in the rectification of the ellipse. The reigning authority on this subject was the venerable French mathematician Adrien-Marie Legendre. For 40 years, Legendre had dedicated himself to a Herculean task, the systematic study and classification of these obstinate mathematical objects. His work was a masterpiece of diligence and order. He demonstrated that all such integrals, regardless of their complexity, could be reduced to one of three canonical forms, a heroic act of organization that brought a semblance of structure to a chaotic field. Legendre had, in essence, created a comprehensive atlas of this new territory, mapping its features with unparalleled devotion. He had tabulated their numerical values and uncovered many of their properties. His life's work represented the absolute pinnacle of what could be achieved with the existing mathematical tools. The integrals themselves remained the central objects of study, their values computed and their relationships catalogued. Jacobi's revolutionary insight was one of profound, almost deceptive, simplicity. He proposed a radical change in perspective, a conceptual inversion of the entire problem. The approach is best understood through an analogy with the far simpler trigonometric functions. The arcsine of x, for instance, is defined by an integral, the integral from 0 to x of 1 over the square root of 1 minus t squared with respect to t. While this integral defines the function, its properties are cumbersome to derive directly. The genius of trigonometry lies in studying its inverse. If u equals the arcsine of x, then x equals the sine of u. The sine function possesses elegant properties. It is periodic, it oscillates smoothly, and it satisfies a simple second-order differential equation. Jacobi applied this exact logic to Legender's far more complex elliptic integrals. He considered the integral u as a function of its upper limit, which he called the amplitude. Then he inverted the relationship. He began to investigate the properties of the amplitude as a function of u. This single conceptual leap changed everything. The functions that emerged from this inversion, which he christened elliptic functions, were entirely new entities in the mathematical world. They were the generalization of the trigonometric functions that mathematicians had long sought. In his 1829 masterwork, the Fundamenta Nova Theoriae Functionum Ellipticarum, or New Foundations of the Theory of Elliptic Functions, Jacobi laid out the complete architecture of this new world. The book, composed entirely in Latin, was an electrifying announcement of a new branch of analysis. Within its pages, he introduced his three primary functions, which we now know as the Jacobi elliptic functions, SNAM, CNU, and DNU. The names were mnemonics for sine amplitude, cosine amplitude, and delta amplitude, linking them to their origins in Legender's work, while signaling their status as a new, more fundamental triumvirate. The most astonishing property of these functions was their periodicity. The familiar trigonometric functions, like sine and cosine, are singly periodic. They repeat their values along the real number line at a fixed interval, 2 pi. Jacobi's elliptic functions revealed a far richer, more complex symmetry. They were doubly periodic. This meant they possessed two distinct periods, say omega-1 and omega-2, such that the ratio of the two periods is a complex number. A function phi of z is doubly periodic if f of z plus omega-1 equals f of z, and f of z plus omega-2 also equals f of z. Consequently, the function's values repeat across the complex plane in a two-dimensional lattice, a pattern akin to an infinite, intricate wallpaper design. This discovery moved the entire field of analysis from the one-dimensional real line into the two-dimensional complex plane, opening up vast new continents for exploration. This breakthrough occurred in a remarkable period of simultaneous discovery. In Norway, the brilliant and tragically short-lived Niels Henrik Abel had independently arrived at the same core idea of inverting the elliptic integral. The two mathematicians, working in relative isolation, had converged on the same revolutionary concept. When Jacobi learned of Abel's work, he was quick to acknowledge his rival's genius, famously writing to Legendary to accelerate the publication of his own Fundamenta Nova while giving full credit to Abel's parallel discoveries. Upon reading Abel's posthumously published Paris manuscript, Jacobi's admiration was unbounded. He declared it a work above my praise, as it is above my works, a rare and poignant expression of profound intellectual respect. The legacy of this conquest is immense and continues to shape our world in tangible ways. The theory of elliptic functions and the elliptic curves to which they are related became central pillars of number theory and algebraic geometry in the 20th century. Their deep structural properties were essential to Andrew Wiles' celebrated 1994 proof of Fermat's last theorem, solving a problem that had tantalized mathematicians for over 3 centuries. In a more practical domain, the intricate algebraic structure of elliptic curves forms the bedrock of modern public key cryptography. The security protocols protecting global financial transactions, government communications, and private data rely on the difficulty of solving problems on these curves. The abstract patterns Jacobi first discerned in the complex plane, born from his re-examination of pendulum motion and the shape of an ellipse, now serve as the invisible guardians of our digital civilization. With the properties of these new functions established, a subsequent challenge emerged. To make the theory truly practical and computationally tractable, Jacobi required a deeper, more elementary set of building blocks. He needed an analytic engine capable of constructing his elliptic functions with the same facility that infinite series construct sine and cosine. This quest for a foundational toolkit would lead him to his next great creation, the Jacobi theta functions. With the properties of these new functions established, a subsequent challenge emerged. To make the theory truly practical and computationally tractable, Jacobi required a deeper, more elementary set of building blocks. He needed an analytic engine capable of constructing his elliptic functions with the same facility that infinite series construct sine and cosine. This quest for a foundational toolkit would lead him to his next great creation, the Jacobi theta functions. The predicament facing Jacobi was one of profound architectural significance. He had charted the behavior of his new elliptic functions, understanding their periodicities and their poles, yet a direct constructive method for their evaluation remained elusive. The definitions, while elegant, were implicit. They describe what the functions did, their essential symmetries in the complex plane, but offered a cumbersome path to calculating their value at a given point. The situation was akin to possessing a detailed blueprint for a grand cathedral, while lacking the means to quarry and shape the individual stones. For the edifice of elliptic function theory to become a workable, applicable branch of mathematics, a supply of fundamental computable components was essential. The trigonometric functions had their Taylor series, infinite sums of powers that allow for their approximation to any desired degree of accuracy. Jacobi sought an analogous foundation for his own doubly periodic creations, his solution arriving with characteristic brilliance in his 1829 masterpiece Fundamenta Nova Theoria Functionum Ellipticarum, was the introduction of a family of 4 remarkable functions, the theta functions. These are functions of 2 complex variables, typically denoted z and tau, and are defined by exceptionally fast converging infinite series. The structure of these series is a marvel of economy and power. Consider, for instance, the third theta function, often written as theta sub 3 of z and tau. It is defined as the infinite summation from n equals negative infinity to positive infinity of the term q to the power of n squared, multiplied by the exponential of 2 pi I n z. Here, the parameter q, called the gnome, is itself a function of the second variable, tau, defined as e to the power of pi I tau. The genius of this construction lies in its utility. Jacobi demonstrated that each of his primary elliptic functions, the sine amplitude sin, the cosine amplitude cn, and the delta amplitude dn, could be expressed as a simple, elegant ratio of 2 of these theta functions. The complex and somewhat opaque nature of an elliptic function
was thereby resolved into the relationship between two more fundamental, more cleanly behaved objects. This was the algorithmic engine he had been seeking. It provided a direct, computational pathway to evaluate an elliptic function. One could now evaluate two theta functions via their rapidly converging series and then compute their quotient. The problem of building the cathedral was solved. Jacobi had manufactured the perfect uniform and easily assembled stones from which the entire structure could be raised. This achievement alone would secure the theta functions a permanent place in the mathematical toolkit. Their role as the foundational elements of elliptic functions provides a powerful example of reductionism in mathematics, where a complex class of objects is understood through a simpler, more primary class. Yet, the properties of the theta functions themselves soon revealed a landscape of mathematical ideas reaching far beyond their original purpose. Jacobi discovered that these functions satisfied a host of remarkable identities and possessed profound symmetries. The most celebrated of these is the Jacobi triple product identity. This formula provides an astonishing connection between the additive world of infinite series and the multiplicative world of infinite products. It states that the series we encountered earlier, the sum from n equals negative infinity to infinity of q to the power of n squared times z to the power of n, is identically equal to an infinite product. Specifically, it equals the product from n equals 1 to infinity of the three-term expression 1 minus q to the power of 2m multiplied by 1 plus z times q to the power of 2m minus 1 multiplied by 1 plus z inverse times q to the power of 2m minus 1. To the uninitiated, the expression may seem a thicket of symbols. To the mathematician, it is a poem. It reveals a hidden bridge between summation and multiplication, two fundamental operations of arithmetic extended into the realm of the infinite. It is a vast generalization of earlier results like Euler's pentagonal number theorem and serves as a cornerstone of the theory of Q-series and combinatorial number theory. It allows one to count partitions of integers in novel ways and unlocks structural truths about numbers by analyzing the functions that generate them. Furthermore, Jacobi investigated how the theta functions behave under transformations of their arguments. He found that they transform in a very specific, elegant way when the parameter tau is altered by transformations from a group known as the modular group. This behavior, where a function transforms according to a predictable rule under a group of symmetries, is the very definition of a modular form. While Jacobi laid the groundwork, the full flowering of this theory would come later. The study of modular forms would become one of the deepest and most fruitful areas of modern number theory, culminating, most famously, in its application by Andrew Wiles in his proof of Fermat's last theorem. The path from Jacobi's analysis of periodic functions to the solution of a centuries-old problem in number theory is a testament to the profound and unexpected unity of mathematics. The legacy of theta functions extends powerfully into the physical sciences. Their periodic nature makes them the natural language for describing phenomena on a torus or a cylinder. A classic example is the problem of heat diffusion on a circular ring. The solution to the heat equation in this setting, describing how temperature evens out over time, is given precisely by a Jacobi theta function, where the parameter tau is related to the time and the thermal diffusivity of the material. What began as a tool for studying abstract integrals became the very function describing a fundamental physical process. In the more esoteric realms of contemporary physics, this utility is amplified. In quantum field theory and string theory, theta functions appear ubiquitously in the calculation of partition functions. A partition function is a master expression that encodes all the possible energy states of a physical system. The modular properties of theta functions, their elegant behavior under symmetry transformations, are essential for ensuring the mathematical consistency of these theories, particularly in string theory, where they help manage the infinities that arise in calculations of particle interactions. From a tool for computation, to a cornerstone of number theory, to a key element in describing the fundamental nature of reality, the journey of the theta function is a microcosm of mathematical discovery itself. Jacobi's creation of this analytic machinery was a pivotal moment. He forged a set of tools that were both immensely practical for his immediate goals and possessed of an internal structure so rich that it would fuel inquiry for the next 2 centuries. The theta functions stand as a bridge, connecting the classical world of complex analysis with the modern landscapes of theoretical physics and number theory. Having constructed this powerful engine for analyzing functions of a single complex variable, Jacobi's attention would also turn to a different sort of challenge, one rooted in the geometry of many dimensions. He would seek a universal language to describe how spaces themselves stretch and compress under transformation, a pursuit that would lead him to develop an algebraic tool of comparable importance. The creation of a new analytic machinery, as with the theta functions, represents a profound intellectual achievement. It equips the mathematical world with tools of immense practical power and deep internal structure, fueling inquiry for generations. Having forged this engine for exploring functions of a single complex variable, Jacobi's attention also turned toward a different sort of challenge, one rooted in the geometry of many dimensions. He sought a universal language to describe how spaces themselves stretch and compress under transformation, a pursuit that would lead him to develop an algebraic tool of comparable importance. This new endeavor addressed a problem as fundamental as it was pervasive in the physics and mathematics of the early 19th century. The world as described by science is a world of multiple, interacting variables. To analyze the flow of heat, the stresses within a solid body, or the gravitational field of an irregularly shaped planet, one must frequently shift perspective. A problem that is intractable in one coordinate system might become elegantly simple in another. The familiar transformation from Cartesian coordinates x and y to polar coordinates r and theta was a well-known case. Physicists and mathematicians understood that to correctly calculate an area in this new system, an extra factor of r was required in the integral. This factor, however, was typically derived through bespoke geometrical arguments, a diagram-based proof showing how a small Cartesian rectangle maps to a curved polar wedge. Each new coordinate system required its own unique, often cumbersome, derivation. What was missing was a general, algebraic machine that could automatically produce the correct scaling factor for any conceivable transformation in any number of dimensions. Jacobi's solution was a work of profound structural insight. He recognized that the key to understanding a complex, non-linear transformation at a local level lay in its linear approximation. For any smooth mapping from one space to another, say from coordinates x and y to new coordinates u and v, the essential information about local stretching and shearing is contained in the rates of change. His crucial step was to organize these rates of change into a single, coherent object, a matrix. This array, which we now call the Jacobian matrix, contains all the first-order partial derivatives of the transformation functions. For our two-dimensional example, the matrix would be a 2x2 grid. The first row contains the partial derivative of u with respect to x, and the partial derivative of u with respect to y. The second row contains the partial derivative of v with respect to x, and the partial derivative of v with respect to y. This matrix is a complete local portrait of the transformation. It is the best linear map that approximates the behavior of the original, more complex function in the immediate neighborhood of a point. It tells you precisely how an infinitesimal vector pointing in the x direction is changed, and how a vector in the y direction is changed. By the principle of linearity, it therefore describes the transformation of any infinitesimal shape. While the idea of a functional determinant had appeared in isolated contexts, for instance within Cauchy's work on elasticity, these were applications tailored to specific problems. Jacobi's contribution was the elevation of this concept into a general, systematic principle of multivariable analysis. He gave it a name, the functional determinant, and established its universal properties. From this matrix of derivatives, a single, profoundly meaningful quantity is extracted, its determinant. This scalar value, the Jacobian determinant, distills the matrix's geometric essence into a measure of volume scaling. Its absolute value represents the factor by which an infinitesimal area or volume is magnified or shrunk by the transformation at that specific point. If the Jacobian determinant at a point is 5, it means a tiny square around that point in the original space is mapped to a parallelogram in the new space with 5 times the area. If the value is 1/2, the area is halved. A determinant of 0 is particularly telling. It signals a point of singularity where the transformation collapses a region of some dimension into a region of a lower dimension, like projecting a 3-dimensional object onto a 2-dimensional plane. The sign of the determinant carries its own geometric meaning, indicating whether the transformation preserves or reverses orientation, akin to mapping a right hand to a left hand. With this tool, the change of variables in multiple integrals became a matter of elegant, algorithmic procedure. The old ad hoc geometric arguments were replaced by a single powerful formula. To transform an integral from one coordinate system to another, one simply multiplies the function, expressed in the new coordinates, by the absolute value of the Jacobian determinant. The mysterious factor of r in the transition to polar coordinates is revealed to be the result of a simple calculation. The determinant of the matrix, whose entries are the partial derivatives of x equals r cosine theta and y equals r sine theta, with respect to r and theta. The calculation yields precisely r. The same procedure works for cylindrical coordinates, spherical coordinates, or any other esoteric system a physicist or engineer might invent. Jacobi had provided the universal Rosetta Stone for translating the language of integration between different geometric worlds. The implications of this discovery radiate throughout modern science. The Jacobian determinant is a cornerstone of undergraduate multivariable calculus, the first genuinely powerful tool students learn for mastering higher dimensional integrals. In physics, it is indispensable in continuum mechanics, describing the deformation of materials, and in fluid dynamics, tracking the expansion and compression of fluid elements. In statistics, it is the essential ingredient for finding the probability distribution of a function of random variables, a task central to modeling and inference. In robotics, the Jacobian matrix relates the velocities of the joints of a robotic arm to the velocity of its endpoint in space, a fundamental calculation for control. Economists use it in general equilibrium models to understand how changes in prices ripple through a complex, interconnected system. In formalizing the functional determinant, Jacobi created more than a calculational convenience. He supplied a fundamental piece of syntax for the language of geometry and analysis. He demonstrated how a concept from algebra, the determinant, could encapsulate a deep geometric truth about the nature of space under transformation. This ability to find unifying algebraic structures that govern disparate phenomena was a hallmark of his genius. Having crafted a language to describe the geometry of space, he would soon turn his attention to an even more abstract and dynamic realm, seeking a similar unifying formalism for the very laws of motion through time. This impulse toward grand unification, having provided a powerful language for the geometry of static space, found its ultimate expression in the dynamic universe of mechanics. The intellectual landscape of early 19th century physics was dominated by the framework laid down by Joseph Louis Lagrange. His mechanics was a triumph of analytical reason, recasting Newton's laws into a system of elegant, generalized equations of motion. For any given mechanical system, one could write down the Lagrangian, a function representing the difference between kinetic and potential energy. The principle of least action then yielded a set of second-order ordinary differential equations, one for each degree of freedom of the system. Solving these equations would, in principle, describe the complete trajectory of the system through time. The framework was magnificent in its universality. Its practical application, however, presented formidable difficulties. For a system of even moderate complexity, the number of coupled differential equations could become overwhelming, their solutions demanding immense calculational labor. The very structure of the problem, focusing on the moment-to-moment evolution of individual coordinates, seemed to obscure a deeper, more integrated picture of the system's overall behavior. The challenge for the next generation of mathematical physicists was to find a new perspective, a method that could penetrate this thicket of equations to reveal the holistic principles governing motion. The first crucial step in this direction came from the Irish polymath William Rowan Hamilton. He reformulated mechanics by introducing the concept of phase space, an abstract space whose coordinates are the generalized positions and their corresponding momenta. This led to Hamilton's equations, a system of first-order ordinary differential equations that were in many ways more symmetric and profound than Lagrange's. Within this new framework, Hamilton began to explore the idea of a single central function whose properties could determine the system's entire dynamical history. He had laid the conceptual groundwork. It fell to Jacobi to seize upon these ideas, refine them, and erect upon them a theoretical edifice of breathtaking power and elegance. Jacobi's contribution was to create a complete and systematic theory centered on what is now known as the Hamilton-Jacobi equation. He demonstrated that the entire problem of solving the many equations of motion in Hamilton's or Lagrange's schemes could be replaced by the task of solving a single, first-order partial differential equation. This equation governs a scalar function, Hamilton's principal function, typically denoted S, which depends on the system's coordinates, time, and a set of integration constants. The equation itself takes the form the Hamiltonian of the system plus the partial derivative of the function S with respect to time equals 0. The profound insight lies in how the Hamiltonian is treated. It is a function of coordinates, momenta, and time. Jacobi showed that the momenta themselves could be expressed as the partial derivatives of this same function, S, with respect to their corresponding coordinates. The result is a single equation where the unknown is the function S. Once this master function is found, the dynamics of the system are completely unlocked. The solution contains all possible trajectories. The original coordinates and momenta of the system can be recovered through a series of algebraic steps involving derivatives of S with respect to the integration constants. The intricate, time-consuming process of integrating a large system of differential equations was thereby transformed into the problem of finding one special function. It was a paradigm shift of the first order, moving the focus from the path itself to the underlying field that generates all paths. This method is deeply intertwined with Jacobi's parallel work on the theory of canonical transformations. These are coordinate transformations within phase space that preserve the fundamental structure of Hamilton's equations. Jacobi revealed that the function ses is the generating function for a particularly powerful canonical transformation. It is a transformation to a new set of coordinates and momenta which are all constants of motion. In these new privileged coordinates, the system's dynamics become trivial. Nothing changes. The entire complexity of the motion is encoded in the transformation back to the original physical coordinates. The art of solving a dynamical problem became the art of finding the right change of variables, a change of perspective that renders the problem transparent. This provided a systematic, almost algorithmic procedure for achieving what was previously a bespoke and often arduous task. The implications of this formulation extend far beyond the realm of 19th-century mechanics. The Hamilton-Jacobi equation provides the most direct and profound conceptual bridge between the world of classical physics and the strange new world of quantum mechanics that would emerge nearly a century later. When Erwin Schrödinger was developing his wave mechanics in the 1920s, he recognized a deep formal analogy. The Schrödinger equation, a partial differential equation for the quantum wave function in the limit of short wavelengths, mathematically reduces to the Hamilton-Jacobi equation. Jacobi's action function Cs corresponds directly to the phase of the quantum wave function. This connection is fundamental. It demonstrates how the deterministic trajectories of classical mechanics emerge as an approximation from the probabilistic wave-like nature of quantum reality. Jacobi's work, conceived to perfect the classical worldview, paradoxically contained the mathematical key to its successor theory. This legacy continues to flourish in modern science and engineering. In optimal control theory, a field dedicated to finding the best possible way to manage a dynamic system, the central equation is the Hamilton-Jacobi-Bellman equation, a direct generalization of Jacobi's work. It is used to design optimal rocket trajectories, manage economic systems, and devise strategies in robotics. Whenever a problem involves finding an optimal path or strategy over time, the intellectual descendants of the Hamilton-Jacobi equation are almost certain to be found. By seeking a supreme unifying principle for motion, Jacobi had crafted a tool of enduring utility, a mathematical lens through which the fundamental structure of change itself could be understood with unparalleled clarity. His work on mechanics, like his work on elliptic functions and determinants, was a testament to his core belief that the deepest truths of nature are revealed through the discovery of powerful, simplifying, and unifying mathematical structures. This relentless pursuit of unifying mathematical structures continued unabated, even as the structures of Jacobi's own life began to face profound instabilities. The final decade of his career saw his health decline, a slow, wearing deterioration that would have halted a lesser intellect. The political upheavals of 1848, which swept across Europe, added financial precarity to physical frailty. His liberal sympathies and the temporary collapse of the old order led to the suspension of his royal pension from Prussia, a stark reminder that even the most abstract of minds remains tethered to the caprices of state and fortune. Though the pension was eventually restored, due in large part to the intervention of Alexander von Humboldt, the period was one of profound uncertainty. Yet, through it all, his intellectual output remained prodigious. His mind, a finely tuned instrument for algebraic transformation and analytical discovery, continued its work. His life, a brilliant trajectory of intellectual ascent, was ultimately cut short by an adversary indifferent to mathematical eminence. An infection of smallpox claimed him in February of 1851 at the age of 46. To measure Carl Jacobi's legacy by a catalogue of his theorems is to miss the more profound contribution. While the list of eponyms, the Jacobian, Jacobi elliptic functions, the Hamilton-Jacobi equation, Jacobi polynomials, the Jacobi identity, speaks to an immense and varied body of work. His enduring influence resides in a distinctive style of mathematical thought, a contribution that subsumes any single result. He was perhaps the 19th century's quintessential algorithmic mathematician. He approached the discipline with the mind of a grand strategist, developing powerful general-purpose machinery designed to render entire classes of intractable problems solvable through systematic procedure. Consider the character of his greatest creations. The theory of elliptic functions, in his hands, became a beautiful and intricate engine. The introduction of his theta functions provided a standardized toolkit, a set of fundamental building blocks from which all the necessary elliptic functions could be constructed. A problem involving the arc length of an ellipse or the motion of a pendulum could be translated into the language of these functions, and the vast, regular, and predictable landscape of their properties would guide the way to a solution. The process had the feeling of a well-defined protocol. One inputs a difficult integral, and through the machinery of theta functions and their myriad identities, a structured answer emerges. The same spirit animates the Jacobian determinant. Before Jacobi, the change of variables in multiple integrals was a chaotic and ad hoc affair, a source of frequent error and conceptual confusion. The Jacobian provided a universal, unambiguous rule. It is a perfect algorithmic device. It gives a precise mechanical recipe for calculating how a volume element transforms under a new coordinate system. The formula, the determinant of the matrix of partial derivatives, is a compact piece of mathematical technology that automates a complex geometric and analytical task. Generations of students in physics and engineering learn this method, applying it with a reliability that belies the deep insight required for its initial formulation. It transforms a conceptual hurdle into a computational step. This procedural ethos finds its highest expression in the Hamilton-Jacobi equation. Here, the entire complex tapestry of a dynamical system's evolution through time is encoded within a single partial differential equation. Solving this one equation for a principal function, called S, effectively solves the entire problem of motion. The coordinates of the system at any future time can be recovered through a set of straightforward differentiations. The method converts the dynamic, evolving problem of mechanics into a static, geometric problem of finding a particular surface in a higher dimensional space. It is the ultimate simplification, a supreme algorithm for dynamics. This perspective reveals Jacobi as a crucial transitional figure, a bridge between the problem-oriented analysis of the 18th century and the structural abstraction of the 20th. His work prefigured the rise of modern algebra and the computational thinking that defines our own era. By focusing on the operational properties of his mathematical objects, the addition theorems for elliptic functions, the algebraic rules for determinants, the transformative power of his canonical equations, he was implicitly studying the underlying structures themselves. He was less concerned with a single number or a specific curve, and more interested in the family of transformations that governed them. This is the very soul of abstract algebra, which seeks to understand systems based on the rules of their internal operations. His famous dictum, "Man muss immer umkehren," or "one must always invert," is often cited in the context of his work on elliptic integrals, where he inverted the function to discover the doubly periodic elliptic functions. But the phrase captures a deeper philosophical orientation. It is an instruction to reframe the problem, to find a new perspective from which the solution becomes transparent. It is an algorithmic command: if one path is blocked, find the systematic transformation that creates a new, clearer path. This principle of inversion, of seeking a transformative key, is the foundational logic behind so much of modern mathematics and theoretical physics, from Fourier transforms to the dualities that permeate string theory. In an age of heroic mathematical figures of Gauss, the prince of mathematicians, with his profound and often inscrutable depths, and of Cauchy, the rigorous builder of foundations, Jacobi carved out a unique and enduring identity. He was the great simplifier, the architect of elegant and powerful methods. His genius was to see the general in the specific, to extract from a thorny problem a beautiful and reusable piece of intellectual machinery. He left behind a workshop filled with tools of astonishing power and versatility. His legacy is felt whenever a physicist uses the Hamilton-Jacobi equation to explore quantum field theory, whenever an engineer applies the Jacobian to design a robotic arm, and whenever a mathematician marvels at the crystalline structure of modular forms descended from his elliptic functions. Carl Gustav Jacob Jacobi, in his relentless quest for calculable, systematic and unifying principles, helped to forge the very character of modern mathematical science, leaving an inheritance of algorithmic elegance that continues to empower and inspire.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.